In August 2023, an Indian spacecraft named Chandrayaan-3 touched down approximately 600 kilometers from the lunar South Pole, becoming the first vehicle in history to land softly in that region of the moon. 4 days earlier, a Russian spacecraft named Luna 25 had attempted to land in approximately the same area and had crashed into the surface at high velocity, ending a mission that had been in development in various forms for nearly half a century. 5 months later, in January 2024, a Japanese spacecraft named SLIM landed on the moon with a positional accuracy of approximately 100 meters against the target site, a precision improvement of roughly an order of magnitude over the landing accuracy of any previous lunar mission. In February of the same year, an American commercial spacecraft named Odysseus, built by a company called Intuitive Machines under contract to NASA, became the first American vehicle to land on the lunar surface since Apollo 17 in December 1972. In June 2024, a Chinese spacecraft named Chang'e 6 returned to Earth carrying approximately 1,900 grams of material from the far side of the moon, the first lunar far side samples ever brought back to Earth, and the result of a sample return campaign that the Chinese space program has been executing on schedule, mission after mission, for more than 15 years. 5 lunar missions by 5 different actors across a single 10-month window. None of them was a duplication of any previous mission. Each of them established a capability, a destination, or a sample type that no previous mission had established. And the 10-month window in which they occurred was not an unusual concentration of lunar activity. It was, by the metrics that matter for the analysis I'm about to lay out, a representative sample of the current operational tempo. This is a video about why that operational tempo exists. It is a video about the political and economic structure of what is happening at the moon right now, about the actors who are conducting that activity and the objectives they are pursuing, about the causes that have converged in approximately the last decade to produce the current period, and about the specific ways the period could break in the next 10 to 15 years. The default framing for this topic is the framing of a new space race, with the implicit reference to the Apollo-era race between the United States and the Soviet Union. The framing is intuitive, and I'll spend the first section of this video addressing what it captures and what it misses, because the gap between the two is the entry point into understanding what the current period actually is. After that section, the rest of the video moves to the substance, who the actors are, what they're building, why now, and what could go wrong. I want to be careful here because the Apollo analogy is not arbitrary. It captures something real, 2 major powers, a destination beyond Earth, a coordinated buildup, a political dimension to the technical activity. Those parallels are present, and the framing's intuitive appeal comes from the fact that they are present. The next 4 sections of this video describe what the current period actually is. This section is establishing why the Apollo framing, despite its intuitive appeal, captures less of that reality than it appears to. Consider first the basic structural fact about Apollo. Apollo was a program with a defined endpoint: land Americans on the moon and return them safely before the end of the 1960s, and a defined competitor, the Soviet Union, whose parallel program was understood to be racing against the American program toward the same endpoint. When the American program achieved the endpoint in July 1969 and demonstrated repeatability through 5 additional landings over the following 3 years, the program effectively concluded. The last crewed lunar landing was Apollo 17 in December 1972. And no human has returned to the lunar surface in the more than half-century since. The Soviet crewed program, which had been racing toward the same endpoint and had suffered repeated failures of its N-1 super heavy launch vehicle, was effectively abandoned in the same period. This is not the structure of what is happening now. The current period has no defined endpoint of the first to plant the flag variety, because the flag has already been planted 6 times by one of the current actors. The current activity is structured instead around sustained operational presence at specific locations on the lunar surface, primarily at the South Pole, on a timescale measured in decades rather than in the 4 to 5 year sprint that defined Apollo. The objective is not the achievement and departure sequence that Apollo executed, but the establishment and maintenance sequence that the current programs are working toward, which is a structurally different kind of program with structurally different success criteria. Consider second, the actor count. Apollo was a 2-actor program in any operationally meaningful sense, the American program and the Soviet program, with no other country fielding a crewed lunar capability and only a small handful of other countries fielding any lunar capability at all. The current period has approximately a dozen actors with active lunar programs, of which 5 have demonstrated operational lunar capability in the last 5 years, and several others are scheduled to do so within the next 2 or 3. The actor count is not a marginal expansion over the Apollo configuration, but an order of magnitude change in the participating actor base, and the multi-actor configuration produces strategic, legal, and operational dynamics that the bipolar Apollo configuration did not produce. Consider third, the role of the commercial sector. Apollo was executed almost entirely by government agencies and their direct contractors, with the contractors operating under cost-plus arrangements that left strategic and operational decisions firmly in government hands. The current period involves a commercial sector that is increasingly setting the pace of lunar logistics, with companies including SpaceX, Blue Origin, Intuitive Machines, Astrobotic, Firefly, and others, building lunar landers, lunar logistics services, and in some cases lunar crewed mission capability under fixed-price contracts that leave substantial strategic latitude to the commercial actors. The commercial sector's structural role in the current period has no Apollo-era counterpart, and the strategic dynamics the commercial role produces, including the dependence of national programs on the operational success of private companies, are dynamics the Apollo framing does not capture. Consider fourth, the funding profile. Apollo at its peak consumed approximately 4% of the federal budget, a funding level so far above the current NASA budget share that the comparison is barely meaningful. The current Artemis program, which is the closest current analog to Apollo within the American space program, consumes approximately 0.3% of the federal budget, an order of magnitude below the Apollo peak. The funding level difference produces a programmatic tempo difference. The current program absorbs slippage and delay, where Apollo's funding profile would not have permitted it. And the difference makes the crash program connotation of the Apollo framing actively misleading for the current period. Consider fifth, the destination specificity. Apollo's landing sites were selected primarily for engineering reasons, relatively flat, well-illuminated equatorial locations that simplified the landing problem and supported the short-duration surface stays the program executed. The current programs are converging on the lunar South Pole, where the engineering problem is substantially harder, but where the economic and operational value is substantially greater because of the water ice deposits in permanently shadowed regions, the long-duration illumination available at specific elevated locations, and the resource extraction potential the combination supports. The destination shift from equatorial Apollo sites to south polar current sites is not a minor variation, but a different category of operational target. And the strategic competition for specific south polar sites has dynamics that the Apollo era site selection process did not produce. The cumulative effect of these five structural differences is that the Apollo framing, applied to the current period, captures only the surface parallels and misses most of the substance. The current period is its own thing, a sustained, multi-actor, commercial supplemented, modestly funded, site-specific positional buildup conducted on a multi-decade timescale at a small set of geographically constrained locations. The next four sections describe that thing on its own. Terms. The American lunar program in its current configuration is the Artemis program, formally initiated in 2017 and operating under the institutional framework that successive administrations have maintained with minor variations through the political cycles of the intervening period. The program's institutional stability across administrations is itself a structural feature worth noting, because it represents a departure from the previous pattern of American crewed spaceflight programs being initiated and canceled in approximate alignment with administration changes. The Artemis program has survived two administration changes intact, with the technical architecture and the coalition structure being maintained through both transitions. The program's technical architecture has three primary components: the Space Launch System's Super Heavy Launch Vehicle, the Orion crewed spacecraft, and the Human Landing System program, which procures crewed lunar landers from commercial contractors under fixed-price contracts. The architecture is supplemented by the Commercial Lunar Payload Services program, which procures uncrewed lunar landers from a separate set of commercial contractors and which has been operationally executing missions since early 2024. The four components together constitute the operational and developmental backbone of the American lunar effort, and each component has distinct strategic and political economy features that warrant separate treatment. The Space Launch System has flown once in November 2022 on the uncrewed Artemis 1 mission that placed an Orion spacecraft into lunar orbit and returned it to Earth. The vehicle's development was costly and slow. The program's history includes substantial schedule slippage and substantial cost growth against the original estimates, and the vehicle's per-launch cost is high enough that the long-term sustainability of an Artemis program built around it has been a subject of ongoing analytical debate within the American space policy community. The vehicle is currently planned to be used through at least Artemis 4, with the architecture beyond that point being subject to ongoing reassessment. The Orion crewed spacecraft is the deep space crewed vehicle that the SLS launches, developed through a joint program between NASA and the European Space Agency that gives the European partners a structural role in every Artemis crewed mission. The European role is worth flagging because it represents a coalition binding mechanism. The European participation in Orion is not contingent on any single mission, and is therefore harder to unwind through political cycles than the partner-by-partner arrangements typical of earlier space programs. The Human Landing System program is the procurement mechanism by which the American program acquires crewed lunar landers, and it is the component of the program most directly exposed to the commercial sector's operational performance. The program has issued contracts to two prime contractors, SpaceX for the Starship Human Landing System and Blue Origin for the Blue Moon lander. The two-vendor approach is a deliberate insurance strategy against the failure or extended delay of either contractor's development, and it represents an institutional learning from the earlier Commercial Crew program, in which the same two-vendor approach was applied to low Earth orbit crewed access. The Starship development is the specific commercial sector dependency that carries the highest schedule risk for the American program's current crewed landing timeline. The vehicle is in active development and testing, with substantial progress demonstrated through 2024 and 2025. But the development trajectory has exhibited the slippage profile typical of novel super heavy launch vehicle programs and the specific operational capabilities required for the lunar landing mission, particularly orbital propellant transfer at the scale Starship requires, have not yet been demonstrated at operational reliability. The schedule risk is non-trivial and is the single largest source of uncertainty in the American crewed landing timeline. The Commercial Lunar Payload Services Program is the institutional innovation that most distinguishes the current American program from its predecessors. The program procures uncrewed lunar lander services from a roster of approximately a dozen contracted commercial providers, with individual mission contracts in the range of approximately $70 to $150 million, a cost profile roughly an order of magnitude below traditional government-led lunar missions of comparable scope. The cost reduction is achieved by transferring substantial mission risk to the commercial providers, who are responsible for vehicle development and operations, and who are paid on a milestone basis that includes substantial risk of partial or complete non-payment in the event of mission failure. The political economy of the CLPS structure deserves explicit treatment because it explains the otherwise puzzling pattern of mission outcomes the program has produced. The first CLPS mission, conducted by Astrobotic in January 2024, suffered a propellant system failure shortly after launch and did not reach the lunar surface. The second mission, conducted by Intuitive Machines in February 2024, landed but tipped over on touchdown and operated for a limited duration. Subsequent missions have produced a mixed record of full successes, partial successes, and failures. The mission-by-mission failure rate is, by traditional government program standards, unacceptable. By the standards of the program's actual design intent, however, the failure rate is approximately what the program assumed and accepted as a structural feature of the cost reduction it was achieving. The trade is the trade that the program's architects made explicitly. Accept a higher mission-by-mission failure rate in exchange for an order of magnitude cost reduction and a substantially higher mission cadence. The trade is rational on the program's portfolio terms because the total scientific and operational value extracted per dollar across the program's missions is higher under the high cadence, high failure rate profile than it would be under the low cadence, low failure rate profile that traditional procurement would have produced. The trade is also producing a commercial lander industry that is gaining operational experience at a rate that no government-led program could have produced. And the industry's long-term capability development is a strategic asset whose value is not captured in the per-mission accounting. The Artemis Accords are the diplomatic framework through which the American program organizes its international partnerships. The Accords are a set of non-binding principles concerning lunar operations, including provisions on transparency, interoperability, peaceful use, and the establishment of safety zones around active operations that signatory countries endorse as a condition of substantive participation in the Artemis program. The signatory count has grown from the initial 8 in 2020 to more than 40 by mid-2025, and the signatory list includes most of the major spacefaring countries except for China and Russia, both of which have publicly objected to specific provisions and have organized a parallel coalition under a different framework. The Accord's strategic function is to establish a set of operational norms that, if widely adopted, would structure the lunar operations environment in ways favorable to the American coalition's interests. The safety zone provisions are the specific element most relevant to the South polar competition, because the provisions, if operationally established, would protect first mover positions at specific sites against subsequent interference. The Accord's status as non-binding principles rather than as binding treaty obligations is a deliberate design choice. The framework can be expanded and adapted faster than treaty negotiation would permit, at the cost of weaker enforcement mechanisms than treaty obligations would provide. The American program's slippage profile is a specific feature worth addressing, because the institutional handling of slippage differs from earlier programs in ways that have strategic consequences. The Artemis II mission, originally scheduled for 2023, has slipped to a current target in early 2026. The Artemis III crewed landing, originally scheduled for 2024, has slipped to a current target in mid to late 2027, with substantial probability of further slippage. The slippage is significant in absolute terms, but the program has absorbed the slippage without producing the program of crisis dynamics that comparable slippage on earlier programs has produced. The absorption capacity reflects the program's lower funding share. There is no equivalent of the Apollo-era political pressure to maintain a specific schedule at any cost, and the institutional learning from earlier programs that has produced more realistic baseline schedules and more honest slippage accounting. The composite assessment of the American program is that it is operationally proceeding on a slipping but real timeline towards sustained crewed lunar presence in the late 2020s and early 2030s. The program is exposed to specific commercial sector risks, particularly the Starship development, and to specific funding trajectory risks across future political cycles, but the program's institutional structure has demonstrated substantially more resilience than its predecessors, and the coalition the Artemis Accords have built provides a substantial strategic asset that is not easily replicated. The Chinese lunar program is the second of the two major actor programs in the current period, and it operates on a structurally different model from the American program in ways that matter for the strategic analysis. The most important structural difference is institutional. The Chinese program is funded through 5-year plan cycles that exhibit substantially lower volatility than the American annual appropriation cycle, and the program's strategic direction is set by an institutional leadership that does not change with administration cycles in the way the American leadership does. The funding stability and leadership continuity advantage is the single most important structural feature distinguishing the Chinese program from the American program, and it produces a programmatic tempo profile that the American program cannot match through institutional means alone. The Chinese program's operational record over the last 15 years is the empirical evidence for the funding stability advantage. The Chang'e series of lunar missions has executed on schedule, mission after mission, with each mission establishing a specific capability that the next mission builds on. Chang'e 1 and Chang'e 2 were lunar orbiters in 2007 and 2010. Chang'e 3 was a lunar surface lander with a rover in 2013, the first soft landing on the moon by any actor since the 1976 Soviet Luna 24 mission. Chang'e 4 was a far-side lander in 2019, the first soft landing on the far side of the moon in history. Chang'e 5 was a near-side sample return in 2020, the first lunar sample return since the 1976 Luna 24 mission. Chang'e 6 was the far-side sample return in 2024 that the cold open addressed, the first lunar far-side sample return in history. The 7-mission sequence, executed across approximately 17 years, exhibits a specific structural property that warrants explicit attention. Each mission established a capability that no previous mission had established, and each mission was executed approximately on the originally announced schedule. The combination, sequential capability extension on schedule, is the operational signature of a program with funding stability, institutional continuity, and disciplined technical execution. The combination is rare in the history of space programs, and it is, in my assessment, the empirical evidence that justifies taking the Chinese program's announced future timeline at higher face value than announced timelines are typically given in space program analysis. The announced future timeline includes Chang'e 7, scheduled for 2026, which is a South Polar Lander and rover mission with resource prospecting instruments. It includes Chang'e 8, scheduled for approximately 2028, which is a South Polar mission with in situ resource utilization technology demonstrations. And it includes the first crewed Chinese lunar landing, scheduled for before 2030, which the Chinese program has stated as a firm objective and which the program's operational record gives reason to take seriously as a target the program has structured itself to meet. The crewed landing architecture is built around two heavy lift launches of the Long March 10 launch vehicle, currently in late-stage development, with one launch delivering the crewed vehicle and one launch delivering the lunar lander to lunar orbit, where the two vehicles rendezvous before the crewed descent. The architecture is technically conservative relative to the American Artemis III architecture, which depends on the substantially more novel Starship and propellant transfer approach, and the conservatism is a deliberate strategic choice that prioritizes schedule reliability over performance margin. The Chinese architecture is more likely to execute on its announced timeline than the American architecture is, by a margin that I would estimate at approximately 15 to 25 percentage points of schedule confidence. And the probability that the first Chinese crewed lunar landing precedes the first American crewed lunar landing of the current period is, by my assessment, between 30 and 45%. The International Lunar Research Station is the multilateral framework through which the Chinese program organizes its international partnerships, and it is the structural counterpart to the American Artemis Accords. The ILRS is a proposed crewed lunar base at the South Pole, with a phased construction timeline targeting initial operations in the early 2030s and expanded operations through the late 2030s. The framework's signatory list, as of mid-2025, includes Russia, Belarus, Pakistan, Azerbaijan, Venezuela, South Africa, Egypt, Thailand, Nicaragua, and several other countries, with the signatory count growing through 2024 and 2025 at a rate that approximately tracks the Artemis Accords growth rate. The strategic significance of the ILRS signatory list is not the per-signatory technical contribution, which is in most cases modest. The significance is the establishment of a parallel coalition structure that, if it consolidates, would produce a bipolar lunar operations environment in which two major coalitions operate at the same general lunar region under different operational frameworks, different norms, and different governance arrangements. The bipolar configuration is not yet a determined outcome. The two coalitions could converge on shared norms, could remain separate but non-conflicting, or could produce operational conflicts at specific sites. But the configuration is the most likely structural outcome of the current trajectory, by my assessment with approximately 60% confidence. The first mover dynamic at the South Polar sites is the specific operational element where the two coalitions' positions most directly intersect, and it is the element I want to address in some detail because it is, in my assessment, the single most underappreciated feature of the current period. The lunar South Pole has a small number of specific sites that combine the three operationally critical features: long-duration illumination at elevated locations, water ice deposits in adjacent permanently shadowed craters, and surface terrain compatible with sustained operations, and the sites are not numerous. Estimates of the count of operationally valuable sites vary, but the credible estimates fall in the range of approximately 6 to 15 sites, depending on the specific operational requirements considered. Both major coalitions are targeting approximately the same set of sites because the site's operational value is determined by physical features that are not coalition specific. Both coalitions are operating on timelines that would establish presence at specific sites in approximately the same window, the late 2020s through the early 2030s. And both coalitions are operating on the implicit assumption that first mover establishment at a specific site produces a positional advantage that is durable across the subsequent operational period because the practical difficulty of dislodging or operating in close proximity to an established presence is substantial. The first mover dynamic produces a specific strategic logic that explains the otherwise puzzling tempo of the current period. The actors are not racing toward an achievement and departure endpoint of the Apollo type. They are racing toward establishment and occupation at specific physical sites whose operational value is determined by features that cannot be replicated elsewhere on the lunar surface. The race is, in that sense, a race for real estate, for the specific locations on the lunar South Pole that combine the features required for sustained operations, and the actor who establishes operational presence at a specific site first acquires a durable positional asset that the subsequent actors will have to work around. The composite assessment of the Chinese program is that it is operationally proceeding on an approximately on schedule timeline towards sustained crewed lunar presence at the South Pole in the early to mid-2030s. The program's institutional structure and operational record give its announced timeline substantially higher face validity than announced timelines typically carry in space program analysis, and the probability of the program achieving its principal objectives within approximately the announced window is, by my assessment, in the range of 60 to 75%, substantially higher than the equivalent probability for the American program's principal objectives within its announced window. The two major actor programs are not the totality of the current period. Approximately a dozen other national programs and a substantial commercial sector are operating in the lunar environment, with each of the other actors pursuing distinct objectives and contributing distinct capabilities. The other actors collectively constitute approximately the same fraction of total lunar activity as the two major programs do, and the strategic analysis is incomplete without attention to them. The Indian program, conducted by the Indian Space Research Organization, is the third largest national lunar program by operational capability demonstrated. The Chandrayaan-1 mission in 2008 was the orbital mission that produced the first definitive identification of lunar water. The Chandrayaan-2 mission in 2019 attempted a south polar landing and produced an orbiter that continues to operate, while its lander failed during descent. And the Chandrayaan-3 mission in 2023 executed the south polar landing that the cold open addressed. The program's announced future timeline includes Chandrayaan-4, a sample return mission scheduled for the late 2020s, and a long-term objective of a crewed lunar landing in approximately the 2040 timeframe. The Indian program's strategic positioning is distinct from the two major programs in a specific way that matters for the analysis. The Indian program is not a member of either the Artemis Accords or the ILRS framework in a binding sense. India has signed the Artemis Accords, but has maintained substantial operational independence and is not committed to either coalition as a primary affiliation. The positioning is a deliberate strategic choice that preserves India's ability to participate selectively in the activities of either coalition, and that maintains the program's identity as a sovereign capability rather than as a contributing partner to a larger framework. The positioning may not be sustainable through the operational consolidation of the late 2020s and early 2030s, but it is the current positioning and it represents a third position strategic stance that other smaller actors may eventually emulate. The Japanese program, conducted by JAXA, is the fourth largest national lunar program and is structurally a partner contributor to the Artemis framework. The SLIM mission in January 2024 demonstrated the precision landing capability the cold open addressed. The program's contributions to the Artemis program include the pressurized lunar rover under development with Toyota and contributions to the Lunar Gateway space station. The Japanese program's positioning is the partner contributor positioning that the smaller signatory countries of the Artemis Accords are largely converging on, and the program's specific technical contributions give it substantially greater operational weight within the coalition than its mission count alone would suggest. The European program, conducted by ESA, is the partner contributor whose role in Artemis is structurally embedded through the Orion service module contribution. The European role in every Artemis crewed mission gives the European program a structural position within the coalition that is harder to remove than per-mission partner arrangements would be, and the position represents the strategic value of structural rather than modular partnership contributions. The European program's independent lunar activities are modest by comparison with the structural Artemis contribution. The program conducts science instruments on multiple lunar missions and is developing lunar logistics capabilities. But the structural position is the program's primary lunar strategic asset and is substantially more valuable than the independent activities alone would represent. The Russian program is the actor whose current lunar capability is most discontinuous with its historical lunar capability. The Soviet program of the 1960s and 1970s was operationally capable at a level comparable to the contemporary American program, with the Luna sample return missions and the Lunokhod rovers representing operational achievements that no other actor matched at the time. The Russian program's lunar activity in the post-Soviet period has been substantially diminished, and the August 2023 Luna 25 failure, a mission that had been in development for approximately 40 years and that failed at the descent phase, is the empirical evidence of the operational capability degradation. The Russian program's primary current lunar role is its membership in the ILRS framework, where the program's historical lunar experience contributes legitimacy to the framework, but where the program's current operational contribution is modest. The commercial sector is the actor category whose role in the current period is least precedented and whose strategic significance is most underappreciated. The commercial sector includes approximately a dozen companies with active lunar lander development, of which approximately half have either conducted lunar missions already or are scheduled to do so within the next 2 years. The companies operate primarily under American government contracts through the CLPS and HLS programs, but a substantial fraction of the commercial activity is being funded through private capital and is being directed toward commercial markets that the companies are betting will materialize over the late 2020s and early 2030s. The commercial markets the companies are targeting include lunar logistics services, delivery of payloads to specific lunar destinations under fixed-price contracts, lunar communications and navigation services, the lunar equivalents of the Earth orbit communications and GPS infrastructure that supports terrestrial commerce, lunar resource extraction, initially water ice extraction at south polar sites, eventually with broader resource categories as the operational base expands, and lunar tourism and scientific charter services for non-government customers. The markets are speculative. None of them has the demonstrated demand profile that would justify the investment levels the companies are committing. But the bet the companies are making is that the operational presence the current programs are establishing will produce the demand profile within the investment recovery window. The structural feature of the commercial sector that warrants explicit attention is the dependency relationship the major programs have on commercial operational performance. The American program's crewed landing timeline depends on SpaceX's Starship development. The American program's uncrewed lunar science timeline depends on the CLPS contractor's operational success rate. The Chinese program is developing parallel domestic commercial capability that is structurally similar to the American CLPS model, and that the program is increasingly depending on for the supplementary missions around the Chang'e mainline. The dependency relationship is a structural feature of the current period that has no Apollo-era counterpart, and it produces strategic dynamics, including the exposure of national programs to commercial sector operational failures and bankruptcies, that the analysis of the period must take into account. The structural analysis of the current period has so far described what is happening. This section addresses why it is happening, specifically why the current operational tempo emerged in approximately the last decade rather than at any earlier point in the half-century since Apollo. The answer is not a single cause. It is the convergence of 5 distinct causes, each of which is a necessary condition for the current period and the simultaneous presence of all 5 of which is what distinguishes the current period from earlier periods. The first cause is the launch cost reduction produced by the commercialization of orbital access. The cost of placing a kilogram of mass into low Earth orbit has fallen by approximately an order of magnitude over the last 15 years, driven primarily by the operational deployment of partially reusable launch vehicles by SpaceX and the competitive pressure that capability has produced across the launch industry. The cost reduction is not specifically a lunar enabler. It is a general space activity enabler, but it operates as a lunar enabler because the launch component is a substantial fraction of lunar mission cost, and the launch cost reduction transmits directly to lunar mission cost reduction. This order of magnitude launch cost reduction is a necessary condition for the current period's mission cadence, because the cadence would not be affordable at the launch costs that prevailed before approximately 2015. The second cause is the discovery and characterization of lunar water ice deposits at the South Pole. The existence of lunar water was definitively established by the Chandrayaan-1 mission in 2008 and was further characterized by subsequent orbital and impact missions over the following decade. The water ice deposits transform the strategic value of the lunar South Pole from a region of primarily scientific interest into a region of primarily operational and economic interest, because the water can be electrolyzed to produce hydrogen and oxygen for rocket propellant and life support. The propellant production potential makes the South Pole a candidate location for in-space refueling infrastructure that would substantially reduce the cost of missions beyond the moon, and the strategic value of being the first actor to establish that infrastructure is the specific dynamic driving the first mover competition the previous section addressed. The third cause is the maturation of small spacecraft and commercial component technology, which has substantially reduced the cost and development time of lunar spacecraft below the levels that prevailed in earlier periods. The maturation includes the development of high reliability, commercial off-the-shelf electronics that can be adapted for space operations, the development of small spacecraft propulsion and avionics systems that support lunar missions in vehicle classes that were not previously capable of lunar operations, and the development of commercial-grade software development practices that have substantially reduced the schedule and cost of flight software development. The cumulative effect is that lunar missions can now be conducted by organizations and at budgets that would not have supported lunar missions in earlier periods, and the expanded set of capable actors is a necessary condition for the multi-actor configuration the current period exhibits. The fourth cause is the institutional development of the multi-actor diplomatic frameworks that have made coalition-scale lunar activity organizationally feasible. The Artemis Accords on the one side and the ILRS framework on the other are the specific institutional vehicles through which the major programs have organized their coalitions, and the framework's existence is a necessary condition for the coalition-structured activity the current period exhibits. The frameworks did not exist in their current form before the late 2000s, and the rapid coalition expansion through the early 2020s is the institutional precondition for the multi-actor configuration to operate as a coherent strategic competition rather than as a set of uncoordinated national efforts. The fifth cause is the strategic competitive dynamic between the United States and China that has motivated sustained American commitment to a lunar program at a level the post-Apollo period had not previously sustained. The competitive dynamic is not the cause of the Chinese program. The Chinese program's institutional foundations and operational trajectory were established before the competitive dynamic became politically salient in the United States, but it is a substantial cause of the American program's institutional resilience across administration changes and of the funding commitments that have made the American program operationally viable. The competitive framing is the political mechanism through which the American program has maintained the institutional support that comparable programs in earlier periods did not maintain. And the framing's persistence across political cycles is the specific feature that distinguishes the current American program from the lunar program proposals of the 1990s and 2000s that did not achieve sustained institutional commitment. The five causes are not independent. The launch cost reduction enabled the small spacecraft maturation by lowering the cost of testing new spacecraft designs in orbit. The water ice discovery motivated the institutional framework development by providing the operational objective that justified coalition-scale activity. The competitive dynamic accelerated the institutional development by providing political urgency. The causes interact and reinforce one another, and the reinforcement is part of why the current period emerged as a coherent phenomenon rather than as a set of unrelated developments. But the five causes are individually necessary. Removing any one of them would substantially weaken or eliminate the current period's specific configuration, and the framework's analytical value is the explicit identification of which causes a future analyst should track to predict how the period will evolve. Of the five causes, the first three, launch cost, water ice, small spacecraft maturation, are the necessary conditions that enable the period. The fourth and fifth, institutional frameworks, competitive dynamic, are the timing determining causes that explain why the period emerged when it did, rather than at some earlier or later point. The distinction matters for predicting the period's trajectory. The necessary conditions are largely irreversible. Launch costs are unlikely to rise to pre-2015 levels. The water ice discovery cannot be undiscovered. The small spacecraft technology base will continue to mature. While the timing determining causes are contingent on political and institutional dynamics that can shift on shorter timescales. The period's persistence depends primarily on the timing determining causes remaining in place, and the specific scenarios in which the period could break down are scenarios in which one or both of the timing determining causes substantially weaken. The analysis to this point has described what the current period is and why it exists. This section addresses how the period could fail to produce the operational outcomes its current trajectory is pointing toward. The failure modes are not predictions. The most likely outcome remains the trajectory the previous sections described, but they are the specific configurations that the analysis must take seriously as non-trivial possibilities, and they are the configurations a forward-looking observer should track as the period evolves. The first failure mode is operational conflict at specific south polar sites. The first mover dynamic the third section described creates a structural incentive for actors to establish operational presence at the small set of high-value sites before competing actors do. And the operational presence the actors are establishing is, in the early phases, lightly defended and substantially vulnerable to interference. The interference could take forms ranging from inadvertent, operational activity at a site producing dust or debris that degrades the operations of a previously established presence at an adjacent site, through deliberate but deniable operational activity conducted in ways that produce effects on competing operations without explicit attribution, to explicitly adversarial. The probability of conflict in the inadvertent or deniable range over the next decade is, by my assessment, in the range of 30 to 50%. The probability of explicitly adversarial conflict over the same period is substantially lower but not negligible, in the range of 5 to 15%. The second failure mode is the operational or financial failure of a major commercial sector dependency. The American program's exposure to SpaceX's Starship development is the largest single instance of this failure mode, but the broader exposure across the CLPS contractor base and the equivalent Chinese commercial sector buildup represents a structural vulnerability that the current period's architecture has not previously been tested against. A major commercial sector failure, the bankruptcy of a key contractor, the technical failure of a critical capability development, the prolonged operational unavailability of a vehicle the program timelines depend on, would produce schedule disruptions that the program structures may or may not be able to absorb. The probability of a non-trivial commercial sector failure over the next decade is, by my assessment, in the range of 40 to 60%, with the probability of a failure substantial enough to materially disrupt a major program's principal objectives in the range of 15 to 25%. The third failure mode is the weakening or collapse of the multilateral coalition frameworks. The Artemis Accords and the ILRS framework are non-binding institutional arrangements whose persistence depends on the continued political commitment of their signatory states, and the framework's rapid recent growth could be partially or substantially reversed if political dynamics shift in major signatory states. The most consequential reversal scenarios involve either a substantial American reduction in commitment to the Accords framework following a future administration change, or a substantial reorganization of the Chinese-led coalition driven by changes in the participating states. Either scenario would substantially complicate the coalition scale activity the period's architecture depends on, and the probability of a non-trivial framework weakening over the next decade is, by my assessment, in the range of 25 to 40%. The fourth failure mode covers two related sources of disruption that I'll address together because their dynamics are coupled. The first is a major mission failure with substantial human or strategic consequence, a crewed mission accident producing fatalities, or an uncrewed mission failure producing substantial environmental or operational consequences at a critical site that produces political and institutional consequences sufficient to disrupt the program structure. The second is a substantial shift in the strategic competitive dynamic between the United States and China in either direction. A substantial reduction in the competitive intensity could remove the political mechanism that has sustained the American program's institutional commitment. A substantial increase in the competitive intensity could shift the lunar activity from the structured competition mode the current period exhibits toward a more adversarial mode that the current institutional frameworks are not designed to manage. The combined probability of a disruption from either of these coupled sources over the next decade is, by my assessment, in the range of 20 to 35%, with the consequences being substantially different depending on which specific scenario materializes. The failure modes are not independent of one another. A major commercial sector failure could produce political consequences that weaken the multilateral frameworks. A weakening of the multilateral frameworks could increase the probability of operational conflict at specific sites. An operational conflict could shift the strategic competitive dynamic in ways that further weaken the frameworks. The coupling means that the failure modes' combined probability is lower than the sum of the individual probabilities. Multiple failure modes can be triggered by a single underlying event, but it also means that the consequences of any single failure mode materializing are amplified by the increased probability of subsequent failure modes materializing in cascade. The most consequential scenarios for the period's overall trajectory are not single failure mode scenarios, but cascade scenarios in which an initial failure triggers subsequent failures across multiple modes. The composite assessment of the failure modes is that the current period's most likely trajectory is the trajectory the previous sections described, but the probability of a substantial deviation from that trajectory over the next decade is non-negligible. By my assessment, approximately 30 to 45% probability of at least one failure mode materializing at a level that produces material disruption to the principal program objectives. The probability is not a prediction of failure, it is a calibration of the uncertainty around the central trajectory, and it is the specific reason that forward-looking observers should track the failure mode indicators rather than treat the central trajectory as a settled outcome. The synthesis of the analysis to this point produces a specific picture of the next 10 to 15 years of lunar activity, and I want to lay that picture out explicitly before closing. The picture is not a prediction in the strong sense. The failure modes the previous section identified are non-trivial possibilities that could substantially deviate the trajectory, but it is the configuration that the current trajectory is pointing toward, and that a forward-looking observer should expect as the central case. The central case configuration through approximately 2030 is the establishment of operational presence at the lunar South Pole by both major coalitions, with the first Chinese crewed lunar landing occurring in approximately 2028 or 2029, the first American crewed lunar landing of the current period occurring in approximately the same window with substantial probability of slipping into the early 2030s, and the uncrewed operational tempo continuing at approximately the current cadence of 5 to 8 missions per year across all actors. The CLPS program and its Chinese counterpart will mature into operational commercial lander industries that are conducting routine logistics missions. The precision landing capability the SLIM mission demonstrated will become a standard capability across most actors, and the first in situ resource utilization demonstrations will produce small but operationally meaningful quantities of lunar-derived propellant by approximately 2030. The central case configuration through approximately 2035 is the consolidation of operational presence at specific south polar sites into sustained habitation infrastructure. Both major coalitions will operate habitation facilities supporting periodic crewed visits and continuous robotic operations. The lunar communications and navigation infrastructure the commercial sector is currently developing will be operationally deployed and supporting both coalitions' operations, and the first commercial customers beyond the major government programs will be conducting lunar operations at modest scale. The strategic competitive dynamic between the coalitions will have produced either a consolidated set of operational norms that both coalitions adhere to in practice, the central case, or a bipolar operations environment in which the coalitions operate separately at different sites with limited interaction. The alternative configurations the failure modes could produce are substantially different from the central case in specific ways. The operational conflict alternative produces a period in which the strategic competitive dynamic dominates the operational dynamics, with substantial program resources directed toward defensive and counter-interference capabilities, and with the multilateral frameworks weakened or replaced by more adversarial arrangements. The commercial sector failure alternative produces a period in which the major government programs are operating at substantially reduced cadence and with substantially reduced ambition, with the failed commercial dependency being replaced through extended duration government-led development that delays the principal program objectives by approximately 5 to 10 years. The framework collapse alternative produces a period in which the coalition structures the current period depends on have weakened to the point that the multi-actor activity loses its current coherent strategic character and reverts to a more fragmented set of national efforts. Across all three alternative configurations, the underlying necessary conditions the fifth section identified, launch cost reduction, water ice availability, small spacecraft maturation, remain in place. The alternative configurations are not configurations in which lunar activity ceases or returns to the pre-2015 baseline. They are configurations in which the activity continues but at reduced cadence, reduced ambition, or under different organizational structures than the central case. The floor on lunar activity over the next decade is substantially higher than the floor that prevailed in any earlier period of the post-Apollo era, and the substantial probability of central case execution is layered on top of that elevated floor rather than substituting for it. The specific indicators a forward-looking observer should track to distinguish among the configurations are, in approximate order of leading indicator strength, the operational performance of the Starship development program over the next 2 to 3 years, which is the single largest variable in the American program's schedule trajectory, the execution of the Chang'e 7 and Chang'e 8 missions on their announced schedules, which is the empirical test of whether the Chinese program's institutional advantage continues to translate into operational delivery. The signatory list dynamics of both the Artemis Accords and the ILRS framework, including both additions and any defections, which will indicate the trajectory of the coalition consolidation. The commercial sector financial performance, particularly the funding rounds and operational milestones of the major CLPS contractors and their Chinese counterparts, and the political cycle effects on the major program funding trajectories, particularly the American program's budget treatment across the upcoming administration changes. The indicators are leading rather than coincident, meaning that observers tracking them should expect to be able to distinguish among the configurations approximately 1 to 3 years before the configuration outcomes become operationally manifest. The indicator framework is the specific analytical contribution this video has tried to provide beyond the narrative description of the current period. The framework is the tool for evaluating in real time as the period evolves, whether the trajectory is proceeding along the central case or deviating toward one of the alternative configurations. I want to close on a specific observation about the current period that I think gets lost in most coverage of it, and that I have tried to make the central organizing observation of this video. The current lunar activity is not a race in the Apollo sense, and the Apollo framing actively obscures what the activity is. The activity is the early phase of a sustained positional buildup at specific physical locations whose operational value is determined by features that cannot be replicated elsewhere on the moon. The actors are not racing toward an achievement that one of them will reach first and then leave. They are racing toward establishment at locations that the establishing actor will then occupy for the foreseeable operational future. And the positional advantage the establishing actor acquires is durable across the subsequent period in ways that no Apollo-era achievement was durable. The implication of the positional framing is that the current decade is not a decade in which a question will be answered and the activity will then settle. It is a decade in which the structural configuration of the next several decades of lunar activity will be determined. Which actors will operate at which sites, under which frameworks, with which commercial sector relationships, and with which strategic competitive dynamics governing the interactions among them. The configuration that the current decade produces is the configuration that the lunar operations of the 2040s and 2050s will inherit, and the configuration's specific features will substantially constrain the options available to actors operating in those later periods. That is why the current activity matters at a level beyond the per-mission interest the individual missions can produce. The 5 missions of the 10-month window the Cold Open described, Chandrayaan-3, Luna 25, SLIM, Odysseus, Chang'e 6, are not isolated technical achievements. They are early indicators of a structural configuration being established, and the configuration's eventual form will be one of the substantial determinants of the strategic, economic, and operational environment beyond Earth for the rest of the 21st century. The question is not whether the current activity will continue. The necessary conditions the analysis identified are in place and are not easily reversible, and the activity will continue at substantial cadence regardless of which of the configurations the period eventually settles into. The question is which configuration the activity will settle into, and the indicators the previous section identified are the specific evidence that the next several years will produce. Watch the indicators. The configuration is being determined